So the last speaker for today is Lei. He is an engineer from IBM who helps other people who are developing OpenBMC. He also maintains a few repos in OpenBMC. And he'll be talking about a real example of porting OpenBMC.
Thank you. Okay, so I'm very glad to be here to introduce a real example of porting OpenBMC to a new system. So this work is done by Louis Sun's OpenBMC team at INSPA. So basically, I am helping the team to do this work. So I am Lei. I am OpenPower AE from IBM. So I maintain some OpenBMC repos, and I am proud to say I write some testable code. And Louis Sun is here as well. He manages the OpenBMC team at INSPA. So you have our contacts. So in case if you have any question, you can contact us. In this presentation, I will introduce an example of porting OpenBMC to a new system. It's called FP5280G2 system. Forget about the model name. Let's call it Dubai. It's simple. And so I will introduce the outcome of this work. Then we will go to details of the porting. And at last, I will share the INSPA's future plan on OpenBMC. So the Dubai system is an OpenPower P9 system with AST2500. As a product, it uses AMI BMC, and it has some special Ethernet. It has a dedicated port for BMC and has an NCSI link where the source could be selected by GPL. It could be configured to use an OCP network or use a PCIe network. So on this system, INSPA decided to use OpenBMC on it. Let's see how it goes. For the maybe 1 or 2 months of work, we have a full-featured OpenBMC with a brand new team. So on OpenBMC on this team, it can do power on, power off. It has all the sensors on the motherboard. It can do fan monitors and it can control the fans. It has full IPMI support, and it also has the web UI, the KVM, the Redfish. All these features are ready. So you can see the task here on GitHub. We have completed all such kind of tasks. So how do we do that? We have a nice document at OpenBMC doc. It introduces the whole process of adding a new system. You can check the link there. So the thing to do is add the configures. For example, you need to add a machine layer to build a new machine. Then you need to add the kernel device tree configures. And then you need to add some JSON configures or YAML configures for power on off, for sensors, for fans, for GPLs, for IPMI, and for VPD. And luckily, as an OpenBMC project, we also get some features for free, which is the web UI, the KVM, the Redfish, the OCC, and the event logging. So that's cool. An overview of the commits are these. So all the 24 commits, we have a full function OpenBMC on a new system. So let's go to the details. The first step is to add a machine layer. So we create a meta Dubai layer. We added the configs. The configure will specify the machine, the kernel device tree, and the preferred providers, like some IPMI configs and some other configs. So this is simple. Next step is kernel. We need to have a kernel device tree and add the kernel configs. So for the device tree, Inspire send the whole device tree to the upstream, and Joey helped to merge the device tree. So that's cool because when someone new to kernel development, it is kind of hard for them to do contribution to the upstream. So Joey helped a lot. Then the kernel config. This config mainly adds some new configs for based on the default OpenBMC config, especially for the sensor configs. Like here, we have added two sensors config, an RTC driver and a GPL driver. So this is specific to the Dubai machine. We have to add some new config to kernel. Then we have power on, power off configs. So this is a JSON config. We need to define some GPLs that can be toggled for power on and power off. In this example, the Dubai machine uses a GPL. It uses two GPLs during power on. So when you can see this polarity setting to false, means if you want to power on, you need to toggle the GPL to low. And there's another GPL for the CPLD, the CPLD to tell the BMC the power is okay. So that's in another GPL. So only with the simple definition, we got the feature of system power on and off. And next is the hard part for all the sensors. So on our open power systems, we use Phosphor hardware monitor repo to manage the sensors. And so all these sensors are defined in kernel device tree. So when kernel runs, the sensors are created in the SysFS and the hardware monitor subsystem. So we only need to define the configs, and OpenBMC will automatically start the Phosphor hardware monitor process, the daemon, to read the hardware monitor SysFS attributes and create debug objects for them. Let's see some examples. If you want to define a fan, we know. I forgot to mention that all these paths are related to the kernel device tree. So, for example, if we are going to, you can find a fan controller here. This is that is the kernel device tree path without the .conf. So when kernel starts, this service knows which folder to read the sensors, and we can just define the fan like fan 1, fan 2. It will create two fans with the config, and the PWM target fan sets this fan use the PWM as the target instead of the speed. So if the fan controller wants to set the fan speed, it just sets the PWM instead of the fan speed attribute. The next example is power supply. So you just need to define the label in 1.2 or power 1.2 with the names. That hardware monitor service will create the debug objects for you to present the power supply current and the voltage on the power. And we have the RTC battery voltage. This is a bit special because you see there's a label in which creates a debug object. Then we have gain, we have GPL chip, and we have GPL, and we have interval. This is because to read the battery, we need to toggle the GPL to read the actual voltage. Otherwise, we always read 0. So the GPL configures are telling the hardware monitor service to toggle the GPL before reading the value. And the gain is to get the actual voltage from the sensor reading. The interval specifies that the service only needed to read this sensor a day. Otherwise, if you read the voltage frequently, it can consume the battery. So it drains the battery. That's bad. Then we have temperature sensors. We have an inlet temperature with a warning high temperature with 40 degrees. And we have the critical high temperature of 42 degrees. So when this inlet temperature goes up to 40, we will see the warning signal from the D-bus. And when it goes up to the 42, we got a critical signal from the D-bus. This is the hardware config. So when that config is done, we can check the sensors from D-bus or REST API. For example, we have a fan with the value is like 11, 8, and 70. That is the fan speed. And we have a PSU with 235 volts. That's a PSU input voltage. And we have RTC battery voltage, which is 3 volts. And we have an inlet temperature, which is like about 27 degrees. That's cool. Then we need to define some other things like fan. Fan configures are a bit complicated because we have fan presence check and fan monitor checks. So here is the fan present. We need to provide a YAML config for the fan present. So here we define a fan 0, which it should be checked by a GPL. The GPL input is read from that physical path, and it is pulled by the kernel. And when the GPL is pressed, it means that this fan is present. And then when the GPL is unpressed, the kernel knows the fan is plugged. So this YAML config will tell the forceful fan presence service to detect if the fan is present or not. And fan monitor. Fan monitor is to monitor if the fan speed is within the expected range. So we need to specify some attributes like if the fan had a target. So if a fan had no target, the service will just ignore this fan speed. And if it's true, the fan monitor service will calculate based on this. So if we set a PWM to 100, and the expected speed will be the PWM multiplied with the factor attribute and plus the offset attribute. And that is the expected fan speed. And we have a deviation. So if the speed goes up a little, that's okay. But if it goes up or low too much, we treat the fan as not functional. And we have fan control. Fan control has 3 YAML configs. The first one is to define or detect if a system uses air cooling or the water cooling. For Dubai system, it's just it's easy. It always uses fan cooling. So on this config, we just define to check if the machine is water cooled, and when it's forced, it means it's a fan cooled. The next is fan zone config. This is also simple because the Dubai system only has one fan zone, which is zone 0. And in this config, it defines the full-speed PWM value and the default floor. So and the increased delay and the decreased interval. So in default case, when the system is powered on, it will use the full speed. And when there are no other events, it will use the default floor. So it will decrease the fan speed to PWM 195. And the last fan config is kind of very complicated YAML config, which defines, that's in the next page. The next one is fan control. I just define which fan to control and which target to use. Here we define the fan 0, which is cooling zone is 0, and sensor is fan 0. The target is fan PWM. So in other systems, like Wishbone, it will use fan speed as the target interface. But Dubai use A-speed fan driver, so it uses fan PWM. Next one is a very complicated one. It defines all the events in which case the fan speed should be adjusted by how. So I have two examples here. The first one is to increase the speed based on the zone calls. So if the CPU core value, if the CPU's core temperature is above 73, the fan PWM should be increased by the delta value, which is 11, and it will increase the PWM every 1 second. The configure in the right is configured to decrease the speed. So when the CPU cores are down, is below 70 degrees, it will decrease the PWM by 11 every 1 second. So this is an example. This whole YAML config is kind of large because it will define other cases like dim temperature, and maybe on open power system, it also handles the OCC events. Oh, question? You mean the? Oh, sorry.
The factor parameter?
The interval is defined in another part, which is not in this example. The factor, let me think.
Like millisecond, how often to increase the PWM, maybe? Just go ahead.
Yeah, I mean, the factor here is it is related to this, to the property, because the property is 70,000. It needed to divide the factor to get the 70 degrees. But the info is not shown here, which it is defined in this YAML, but not in this example. Sorry for that. So the interval may be, Brad, do you remember the interval of our fan speed control? I guess it's when it's increased, it will increase every 1 second, and when it's decreased, it decreases every 3 seconds. That's my remember, but I'm not sure. Yeah, it's configured in this YAML. So when we have all the fan YAML configs done, we can see the fan will have the value property, which is the fan speed, and the target property, which is the fan PWM target. So if I manually change the fan PWM target to 128 from 255, the fan speed is decreased about half. That is just a demo of the manual setting of fan PWM. But in reality, this target is set based on the YAML we defined previously. So the next one is GPIO. For open power systems, we always have a GPL from the host CPU to BMC to tell that the host has a problem. It needs check stop. So this config is very simple. It just use the GPL key event and with the key as the GPL value. So when this key is pressed, OpenBMC should start a new systemd target, which is OpenBMC host crash. Okay, so next one is IPMI configs. The IPMI has a lot of config files. So I divided them to 3 recipes. The first one is first IPMI host, which defines the IPMI sensors and inventories and flows. The next one is first IPMI flow. That it contains the flows and extra properties. So this config defines the flow ID to the inventories. And we have the IPMI OEM, which are for inventories. This is kind of complicated. Let's see the examples. First one, if we want to define an IPMI sensor, which maps the dbus object to IPMI, we need to have the sensor ID, which is predefined between the BMC and the host. Then we need to define the interface and the dbus object path. So in this example, we map the dbus object, which is P0 core 0 temperature, to IPMI sensor ID 91. It is a temperature sensor. So we will have a lot of such kind of configs to map all the dbus sensors to IPMI. So an example, if you use IPMI tool to check the sensor list, we see the dim temperature, the CPU core temperature, the unit temperature, etc. Then this is the flow config. The first one is the same. It's a flow ID, and this is the dbus object path. Oh, where is the dbus object path? Oh, there. Sorry about that. So this defines the flow. It should have it should implement these interfaces. So when you use IPMI to check a flow, you see, for example, the CPU will have the manufacture date, the production name, and the serial, and the part number. And if it's a DIM, it should have the manufacturer, the name, the serial. Then we need to specify the inventories. That is kind of simple because we just, the main part is the dbus object path. Oh, sorry. Yeah. And that part is for IPMI. I am not very familiar with that. If you have questions, you can send to mailing list or you can contact Tom and Deepak. They are way more familiar than me. So the next one is the VPD layout. And typically on an open power system, the BMC will have a VPD to store some information. For example, the BMC's model, the BMC's MAC address, etc. And on Dubai system, it uses the BMC. It defines the BMC's serial number, the manufacturer, and it defines the BMC's Ethernet MAC address. So what we need to do is define two configs. One is which kind of dbus objects we should create, and what kind of let's take an example. The through is BMC and Ethernet. So when it reads the BMC, it should read the part number, the serial number, the manufacturer from the VPD's keywords like VP, VS, and VN, and etc. For item, it should read the VPD DR. And when the kernel starts, it will detect the EEPROM, the VPD EEPROM, separated by a comma. It has two. Yes, I think. Yeah, I'm not sure. The path is the object path on dbus in inventory. So when kernel starts and it gets the EEPROM, it will start a service to call the inventory to create the BMC and the Ethernet objects on the dbus, and it will read the contents from the EEPROM. An example is that when the dbus objects are created, if we send a REST API, we get the data like the BMC will have the build date, the manufacturer, the model, etc. And if for the Ethernet, it will have the MAC address with a real MAC address. Then let's talk about some features we got for free from OpenBMC. For to buy the meta layer, it just needed to add the bit-baked recipes to the image packages. Then we will get the features like web UI, the KVM, the Redfish, the OCC, and even the logins. So this is an example of Dubai system with web UI. You can see all these functions are ready, and we got an KVM, the system already booted into the petty boot. So Insert will do some more work on OpenBMC. The first one is switching NCSI source, which just I mentioned before, that the NCSI could use the OCP network or use the PCIe network card. It is configured by a GPL. So currently, OpenBMC does not have this feature. And I think some other system may have this same design on hardware. So if this feature is completed, it could be leveraged to other systems. The next one IPS is working on is PSU firmware update. We are working on this. We have some progress, and we need to continue working on that. Then IPS are also interested in working tasks on PRDM and VRM, which they are doing now. That's great. So that's all from my talk. So any questions? Hey.
What was the toughest part of the porting?
Yeah, sorry?
What was the toughest part, the hardest part of the porting?
Yeah, I guess it should be the IPMI configs because it's kind of complicated, and we need to have 5 different configs. Luckily, the sensor IDs are the same as Romulus, so we can copy the Romulus ones. But if it's a fresh new system, the IPMI YAML config should be the hardest part, in my opinion.
And how long did the port take?
Yeah, I think the whole, let's check the Git commit. Oh. It's like 2 months, including all these commits. But some efforts are for studying because it's a new team. How many people? Maybe Luis, you can share.
about 3 people.
And how many legacy like Romulus you have before? Like, what legacy? Like the IPMI, you said the main purpose that you have already copied it from.
Yeah, for the IPM part, it's lucky we have Romulus to copy.
Okay, but this is
Yeah. So if you are interested about that, I have some other scripts to generate IPMI YAML config based on another in OpenBMC in OpenPower. It's generated from MRW, which is the machine workbook, to a report file, which defines a list of all the IPMI sensors. So I have a utility to convert that report file to the YAML config. But that is not mentioned in this because it's, yeah, if you are interested, we can talk later. Okay, thank you.